Hello, this is the exam for review for organic chemistry for Spring 2020. So we're just going to go through the slides here and show you the things that you're going to need to work on for the exam. So see if it's a little faster. Okay, so one of the things you're going to need to do is figure out how many chiral centers there are. So I'll present a molecule, and you need to let me know. So what you're doing is you're looking at a carbon that has 4 different groups attached. So for this one, and it doesn't necessarily have to be a carbon. It just can be any molecule or any atom, as long as it has 4 different things. If there is, say, a tie, what you can do is then go out one further and see if there's a difference, and keep going out until you either find a difference, or you come to the end of the chain, or you come back onto yourself if it's a ring. If that happens, then those are not the same. If there's no difference between it, or they come back onto itself in a chain or in a ring, excuse me, then those are not. Then it's not a chiral carbon. So for things like this, right? So anything that has a multiple hydrogens on it, you can get rid of. It can't be that, because you have to have 4 different things hanging off of it. So that gives us perhaps this one, right? And so we're looking at a fluorine, a hydrogen, a CH2, and a CH2, right? Those are the same, right? So what we're going to do is then we're going to hop out here and then compare this, CH2 and CH3. Those are different, which means this is different from this, which is different from that, which is different from that. And so this is a chiral center. Okay. Now for this one, if you put in the hydrogens, right? None of these, right, are going to be chiral. None of these 5 are going to be chiral because they have multiple CH2s on them. So the one we're interested is this one here. And so we have a hydrogen, a chlorine, right? A CH2 and a CH2. Well, just like this one, it's a tie. So we're going to move one out one further. Right? So we're going to go CH2, CH2. Compare these two. Well, no, that's the same. And then for here, we're going to look there and say, oh, it's come back onto itself, and so therefore that's not a chiral center. So this molecule is achiral. There's no chiral centers to it. Okay, so once you find, he says, once there is a chiral center, and you have to be able to designate it, how the atoms are arranged in space. Okay? And so the way we're going to do this is, if they're arranged clockwise or to the right, we use the R designation. If they're arranged counterclockwise or to the left, we use the sinister or S designation. Okay, so how do we do this? How do we figure out, how the atoms go around? Well, we have to set priorities of, highest priority, and then 2, and then 3, and then 4 being the lowest priority. Okay, so so we had to set the rules. So the rules are these Kahn-Ingold-Prelog rules, and so what they said is, okay, everything is separated by mass. The heavier you are, the higher the priority you are. Okay? And so what we're going to do is we're going to look at the 4 atoms that are directly attached to them, to that chiral center, and say, okay, can we separate them by weight? So if we can set it, then we do. So with that, and then we're going to be radiating out from, if there's a tie, then we're going to radiate out just like we did. We're looking for chiral centers. As soon as we find a difference, we'll stop. Okay. So if it's say a carbon and a carbon for two of them, what we need to do then is look at, so like for here, right? This would be the number one. You know, this one, or this one. Right? The fluorine's the heaviest, heavier than carbon, but carbons are heavier than hydrogen. So this is going to be number 4. Okay, but we don't know what's going. You know, we don't know what's happening with this. You know, so with this, so we have to look at the bonds and do this so you can see. Right? They both. This one has 2. So each one of these has 2 carbon-carbon bonds. The one here and here. This one, it's the wedge as well as that carbon, the 2 carbon hydrogens. And notice how they're exactly the same, right? And so what we're going to do is then we're going to hop out here. And so for this one has 1 carbon-carbon, 2 carbon hydrogens, and 1 carbon chlorine. Here we've got just the 1 carbon-carbon. So the heaviest bond for this one is carbon-carbon. This one is carbon chlorine. Okay, and so that makes this one. As we're radiating out, we get to this point and we can find a difference. So we're going to set it. And so, okay, and so the priorities go 4, 1, 3, 2. Okay. Now, if you want to, so to say if it's going clockwise or counterclockwise, there's a couple of different ways that you can do this. The first one is if this is probably the more common way of being taught, is you have to get the hydrogen, or I should say the number 4 priority group going away from you. So you got to rotate the molecule, okay, yeah, away. When you do that, then you look to see how things sweep. Okay? So if you're looking at something like, so let me switch the cameras here. Hey everybody. So if you have it something like this, so let's say that the 4 is coming out at you, and then it goes 1, 2, 3. What you need to do is you need to rotate this or flip it or whatever it is, so that it is going away from you. Okay, you have to have the number 4 thing going away, right? And so now it's 1, 2, 3. It's going like this. So, and so it would be going at, in this case, it would be going S, because it's going the as a steering wheel, you would turn the car to the left, and so you would, and so this would be the S designation. Okay. But you have to have the 4 going behind, going away from you. Okay. The other way that you can do this, and this is how I was taught. Okay, is to say, okay, your thumb has to point the same direction as your as the 4 is. Okay, so if it was like this, what you would do is you would have your thumb be up. I'm going to rotate this with that. So remember, this is 1 and this is 2. And what you're going to want to do is have your hand. Let's see, it's pointed how 1 is, and then you're just going to sweep, right? So 2 is over here, 3 is behind. So if you get to 1 to 2, you're good. And so notice how my hand, if I can get this all in frame, is pointing towards the, my fingertips are pointed towards the 1, and then they can sweep over to where the 3 is, right? So it's going to go from here, sweep to 2, and then to 3. So 1, 2, 3. Since I'm sweeping with my left hand, then it is S. Okay, if I try to do that with my left hand, right, or with my right hand, I would go 1 out, some of that, and so wouldn't be able to do it. Okay, So that's how you figure it out. So, and if it's pointed like this, right, your thumb's going to be pointing like this. So 1, 2. So with that, it's pointed, it's pointing out at you, right? It would be 1, 2. Right? So however 4 is going, it's that's where your thumb is. So it's a little weirder, but but you don't have to redraw it. That's the advantage. So we'll go through one of the examples here. So I do like this one. Okay. So for this one, the chiral center is actually right here. Let's do this in red so you can see it. Actually, let's do it purple. So on the exam, I'm going to point out which one it is I want you to deal with. So it's this carbon here. Okay. And so what we're going to be looking at is that CH2, this CH2, this C, okay, because it's attached to a CH3 on this side and there's a CH2 down here, just kind of cut off. But you see, so what's the fourth bond? Well, usually what you have is you're going to have 2 regular bonds, a wedge and a dash. And what's not shown? Well, it's the hydrogen, so that must be the one on the wedge. Okay, so what we're going to do is we're going to compare hydrogen, carbon, carbon, carbon. Okay, and so the carbons are heavier than hydrogen, so we can automatically set this as number 4. Okay, but the problem is, right, there are ties, so we're going to look at this here, here, and here. So for this one, it says 4 carbon-carbon bonds. This one has 2 carbon-carbon, 2 carbon-hydrogen. This one also has 2 carbon-carbon, 2 carbon-hydrogen. Okay. So the heaviest bond is, for each of these, is the carbon-carbon, but this one has 4 of them. Okay, and so this chain right here is going to be a higher priority than either one of those 2. But these 2 are a tie. Okay, so what do? We have to go out one further, right? And so for here, so we go, now we're going to compare this one to this one. Okay, this one to this one. Right, they're both carbon-carbon, so that's a tie. Okay, but this one has 3 carbon-carbon and 1 CH. Okay, this one has 2 carbon-carbon, 2 CH. Okay, and so again, the carbon-carbon is going to be the heavier, but this one has 3 of them. This one only has 2, and so that sets this. That means this side of the ring is a higher priority than that side. So this side would be 2, and this side would be 3. And so if you redraw it, right? Oop, 4, 1, 3, 2. Okay. So if you're going to do steering wheel method, we're going to have to flip. So take this. Right? We're going to have to flip it around like this. Okay. So if this is 1, 2, 3. Right? This, we're going to have to flip it. When this flips, those 2 flip as well. So flip. Okay. And so it then goes to 1, 4, 2, 3, right? And so this is going, notice how it's going clockwise here. So it makes this R. Okay. Now, if you were going to do this with the hand method, okay, I'm going to rotate this just to make it easier on my wrist. But notice how the force coming out at you. So your thumb's going to have to be pointed out. Your fingertips are going to point at 1, which is over here. Right? So 1 to 2. So it's going 1 to 2. Sweeping like this. Okay, and since I'm sweeping with my right hand, it's R. So you can use either method. And there are a bunch of other ones too. So if you can do this one, you can do them all. Okay, you just have to be very disciplined in going and radiating out. Okay, so that you don't miss it. because as soon as you can set the stereochemistry as you radiate out, you do, and that's it. And you stop. Okay. Okay, so for enantiomers, okay, what you need to remember is that enantiomers, their boiling point, melting point solubility, things like that, all of their properties are exactly the same. Okay, there's only two ways that that they're different. The first one is what's called optical activity, and that's how it can rotate. If you have light coming in like this, when it comes out of solution, okay, and so if you have polarized light coming in to a solution of your stuff, when it comes out, the light will be rotated, either like this, clockwise or counterclockwise. Okay, that's one of the ways that it's different. And the ability of a molecule to rotate light, that means it's optically active. Okay, it's just its ability to do that, to rotate the light. Okay, and so the enantiomers are gonna do it equal but opposite direction. So this is one way where they're different. Okay, the other difference is how they interact with other chiral molecules. Okay, so about that. So, but if you have the R, it's going to go one way. If it's the S, it's going to be the other. Okay, so about that. So, if it rotates light clockwise, it's we call that D, or dexter rotation. If it's the L, if it rotates like counterclockwise, we give that the L configuration. Okay, there's no correlation, okay, between R and S and either plus or minus DL. This is sort of a made-up convention. Okay, so this is made up so that everybody talks about the same. This is experimental. Okay, so it's not that R is D and S is L. That's not how it works, because in some, those are two separate things. Okay, now if you have an equal number of the D and the L, or the R and the S, okay, we call that a racemic mixture. Okay, when you can see that designated as a little squiggly line sometimes. I'm not going to throw that at you, but if you ever see that, that's what that means. Okay. If you have a racemic mixture, it's not optically active because it does not rotate the polarized light, because it will, what is it? They basically, the solutions or the molecules cancel each other out. So if the D goes slightly this way, then when the light hits an L, it'll go back, something like that. So so if you have a racemic mixture, it won't rotate the light. Okay. Now you can come in and what is it? You can determine it. So lots of times you'll see a percent. If you buy a chiral molecule, you'll see it as a percent EE. And all that means is it's the difference between the two, and the difference between the two enantiomers. And so percent EE, right? It's just whatever the larger one is minus whatever the smaller one is, just so it's a positive number. So in this case, it's 97% minus 3%. Okay, so the percent EE, right, would be 94%. That's all it is. It's just the difference between the two. How much more of one enantiomer do you have over the other? So if you see percent EE, that's what they're looking at. Now, one of the things that happens with chiral molecules during synthesis is that if you start off with achiral building blocks, so molecules that do not have any chirality to them, so no chiral centers, then the product that you get out at the end is going to be a racemic mixture if you make a new chiral center. So no chiral centers here, no chiral centers here, no chiral centers here. So the molecule that comes out, there is a chiral center that forms right there, but it's going to be a racemic mixture. Half of it's going to be the R, half of it's going to be the S, because there's no way to control it. The hydrogen's coming in one way or the other. Now, the only way that you can do that to set a stereoisomer is to use chiral components. Okay. So in this case, you'd use a chiral catalyst, and so for here, it's here's the chiral catalyst. The other one is, or you can say use an enzyme because it's made up of chiral amino acids, so it is chiral. So you have, if you want to make a chiral center, you want to make just the R version of this, then you have to use chiral building blocks to do it. Okay. Now, if you're trying to compare the two, enantiomers versus diastereomers, okay, the easiest way to do it is to look at how the wedges and dashes have been flipped. So if all of the wedges and dashes have been flipped, even if it's just one, if all of them have, then they're enantiomers. If not all of them, okay, so here we're gonna hold this one steady, right, and then only flip this one. That makes these two diastereomers, so not mirror images. They're stereoisomers that are not mirror images. Right? So with that, so for here, right, so these are right, so these are diastereomers here. Actually, these are diastereomers as well because we're only switching, right? If you compare this one to that one, switching this to this. So these are diastereomers, these are diastereomers, but these are enantiomers, okay? Because we've flipped, we've gone all from all dashes to all wedges. All of them have flipped, so these are enantiomers. So what's the maximum number of potential stereoisomers you have? Well, it's 2 to the n, right? So if you have 4 stereoisomers, you could have a maximum of 16 potential stereoisomers. Okay, if you drew them all out, okay, you'd have 16 different configurations of that molecule. Okay, and the numbers go up really fast, really quickly as you add, because it's an exponential. So as you add an additional one, right? You multiply that number by 2, and it's going to get really big, really fast. Okay. Okay, so a molecule that's meso, okay, it means it has chiral centers, okay, but it has a plane of symmetry, okay, so the molecule is actually overall achiral, okay, and so what happens is, right, there's 2 beautiful chiral centers right here and right here, right, but we have this plane of symmetry, and so if we so if we have it so that they are, let me switch the camera again so you can see this. So if you have right, the 2 let's see, in this case fluorines pointed towards you, okay, its mirror image would be that, okay, where they're both pointing away from you. Okay, notice how I just flipped it. Okay, that means that they are in fact superimposable. So meso just means it has chiral centers, but the molecules themselves cannot have an enantiomer, because if you make the mirror image, it's just the molecules. You're just remaking the molecule just flipped over. Okay, and so it's this really weird sort of exception. It's not something you come across all that often, actually in the lab, but you come across it in textbooks all the time. So, is the molecule chiral or meso? Well, for here, right, you may want to draw on the hydrogens just to remind yourself. Right, there could be. Is there a plane of symmetry right here? Right, so if this bromine looks in the mirror, does it see a bromine over here? No, it sees a chlorine. So there's no plane of symmetry, so there's chiral. So this one's chiral. Here again, you've got, so you've got these 2 chiral centers here, here, and here. Do we have a plane of symmetry? Yep. Right, if this bromine looks into the mirror, right, it's going to see that bromine. Right, if this hydrogen here looks into the mirror, right, it's going to see that hydrogen. If this CH2 looks in the mirror, it's going to see that CH2. And so this one is going to be meso. Now this one is kind of quirky because there is in fact no chiral centers here. And so, right, so you go hydrogen, chlorine, right? CH2, CH2, right? That's a tie. And so then you would go down here and you're gone, come back onto yourself. So with that, so this side of the ring is in fact is the same as that side of the ring, and so this one's actually achiral. Okay, so for Fisher projections, okay, what you have to remember is that the for the horizontal lines, right? Those are the wedges. The vertical lines are all dashes. Okay? So if you rotate it, not a Fisher projection 90 degrees, what you've done is you've flipped the wedges and dashes. Okay, when you do that, you've made the enantiomer. If you rotate it 180 degrees, right, all the wedges are still wedges, all the dashes are still dashes. So they are, it's just the same molecule, just rotated around. But if you look at, so we, not something like that. Now, with cyclic compounds, don't forget that the plane of symmetry for these meso compounds, right, can slice through an atom, right? Can slice through this CH2 here. That's totally fine, okay? So these two don't have a plane of symmetry, right? Because this methyl is going to look in the mirror and see that hydrogen, right? So it'd be like you looking in a mirror and seeing your little brother, right? It's not correct, not a real mirror. But if this methyl looks into the mirror, it's going to see itself. Now, if you want to separate out racemic mixtures, the way you do that, okay, is you make them temporarily into diastereomers. Because remember, with enantiomers, they have the same melting point, same boiling point, same solubility in water and alcohol and hexane and chloroform and whatever with that. And so you're not going to be able to separate them easily. So one of the tricks is to actually make them temporarily into diastereomers. So you add an extra bit onto the molecule that is only R. Okay, so you have the R and the S. If you add an R to this one and add an R to this one, you get an RR and you get an SR. Now these are diastereomers, right? In order for this to be the enantiomer already, it would have to be SS. Okay, so these are diastereomers. Now these you can separate. Okay, so you're going to have your RR bucket. Okay, and you're going to have your SR bucket. Okay, that you can separate out. If you remove this, if you remove that R, this temporary group here, you end up with a bucket of just R, and you have a bucket of just S. Okay, so the way you do it, make a temporary diastereomer, and then do the separation. Now, the chiral center does not have to be on a carbon. Okay, a lone pair can be a group. Okay, and so like for here, right, for this hydrogen, right, we have hydrogen, a lone pair, a methyl, and an ethyl. Those are 4 different things, right? So this is a chiral nitrogen. Now, one of the weird things with nitrogen, as long as it's uncharged, it'll actually spontaneously go between the R and the S version, and it'll invert. It's one of the quirks of nitrogen. Okay, but other atoms don't do this. Okay, so last thing, okay? So cis and trans, right? So with that, so remember cis and trans, it's for here, it's these hydrogens sitting off of, you have to have one hydrogen sitting off the on either side of the alkene. Okay, if they're both pointed down or they're both pointed up, right? It's cis. For trans, you have one up, one down. Okay. So for alkenes, okay, here you can get the E and the Z designation. Okay, and what we're going to do is we're going to slice that double bond. okay, so that we have one carbon on one side, one carbon on the other, okay? And then we're going to look at the two groups hanging off the left carbon and set a priority, like a 1 and a 2, or a high and a low. Okay? And then on the other one, on the other carbon, we're going to do the same thing. We're going to set, you know, a 1 and a 2, or a high and a low. Okay? And then we're going to take a step back and say, are the highs both up? Are they both down? Or is one up, one down? Okay, so are they on the same side? If they are, you know, like they're both up, then it's Z. If they are not on the same side, then, you know, there's one up, one down, then it's E. Okay. So like here, right, this would be an E because the highs are not on the same side. Here, they are on the same side, right? They're both up. Something like that. So, okay. So let's do a, right? So we'll do an example here, right? So I'm going to slice this. Right? So you got the two. So you got. I'm going to have a red carbon and I'll do a green carbon. Okay. So on the green carbon, right? We're going to look at this C. We're going to compare that CH3, that CH2. We're going to compare these two, right? They're both carbons, right? So that's a tie. So this has one carbon, 3 CH. Right? That one has 2 carbon, 2 CH. Okay. So this one has, so the heaviest bond for both of them is carbon-carbon, but this one is heavier, right? And so this one is going to be the high. This is going to have a higher priority than that one. So put the high and the low. So for the red ones, right, it's going to be this CH2 versus that CH2. Okay. So for this one, okay, we have 2 carbon-carbon bonds, 2 CH. Okay. And then this one, we only have 1 carbon-carbon, 2 CH, okay, and then 1 CO bond, right? So we got this one right here. Now the OH, we don't care about that because it's not directly attached to the carbon, okay? For here, we've got the heaviest bond is carbon-carbon. Here it's carbon-oxygen. Oxygen is heavier than carbon, so that makes this one, this side, to be a higher priority than this, so low. Okay, so the high is down. Below, on this one, the high is also down. They're on the same side, so this one is Z. Good luck.